Hello, this is Vlado from ViDiLabs. In this video I will show you how to use the motion blur calculation with the ViDiLabs calculator. In order to explain how we change the exposure in a camera and why, I need to bring up a drawing. So let me explain first the electronic exposure or the shutter in the IP CCTV cameras, and for that matter in all electronic cameras. So electronic exposure is basically decided by the electronics of the camera based on the amount of exposure it gets to the sensor, so that the camera tries to not overexpose it, so that you have enough details in the bright areas, but also not to underexpose it, so you have enough light to produce motion pictures. We are talking about CCTV camera in this case, which means we are assuming that we are producing live streaming from the camera, which is about 25 frames per second in the PAL legacy countries, or 30 frames per second in NTSC legacy countries. So according to the standards, what we consider live streaming is when you have at least 25 frames per second. So once you have 25 frames per second, we call it live streaming, live under inverted commas of course, but it is live streaming, and that means whatever setting and calculation we are doing, we are trying to preserve 25 frames per second. You can have less than that, but in that case that is not compliant with the standards for live streaming. So if you look at this drawing, this is how I can explain the best the electronic exposure and how the control of the length of that is changing, how you can change it. Most of the IP CCTV cameras, not all of them, but most of them, you can control within the camera setup menu, and you can change the actual exposure to be shorter than what the camera comes to be as default, which is 25 frames per second or perhaps 30 frames per second. But you can also extend it and make it to be maybe 10 frames per second, in which case there will be artifacts which I will explain in a few seconds. So the top row here, where it says 25 frames per second, this is just symbolically representing with exposure, so active exposure time. In order to produce 25 frames per second, the exposure length cannot be longer than 40 milliseconds, because when you divide 1/25, you get in 1 second. To have 25 frames per second, you need to have at least, or the longest you can allow for is 40 milliseconds. When I say the longest, that means this is one of the major stumbling blocks why with CCTV cameras that produce live streaming you can't see in low light as much as with, let's say, static camera or fixed camera. You take your photographic camera, you can take very nice pictures in almost total darkness by letting the exposure to be maybe 1 minute or 30 minutes if you want. But certainly for us, in order to produce 25 frames per second, we are limited to 40 milliseconds as the longest exposure we can have. So if we have a normal 25 frames per second camera, that means in this top drawing we are saying that the longest exposure, 40 milliseconds, will guarantee 25 images in that second, which will give you the illusion of motion pictures. So what happens is, if there is more light than is needed, so certainly then the camera can reduce the amount of light getting into the sensor. One way of doing that is if you are using auto iris lens, then the iris of the camera lens will reduce the opening, which means it will increase the f-stop. That will allow less light in the camera. You still produce 25 frames per second, but you reduce the amount of light because iris closes, and by that you still have a decent picture quality. Now another way, which is also very common, it could also work in conjunction with so-called auto iris, which changes the iris, is by electronic shutter being controlled by the camera depending upon the exposure. So in other words, as you can see here in the middle drawing, what we are demonstrating here, if there is too much light, and let's say you've got fixed iris, you can't change the iris for some reason, even if you can, you may still have electronic exposure working. The camera will decide to have, look, I still have too much light, whatever you have done, I need to shorten the exposure. So the camera will then, let's say, shorten to 10 milliseconds. So that's 1/4 of 40 milliseconds. But it will still produce 25 of those frames. So in other words, when you reduce it to 10 milliseconds, as you can see here, where the number 1 appears, you still have plenty of time for the frame to finish exposure, but the camera doesn't expose because the electronic shutter decided to stop at 10 milliseconds. It waits for the next frame. In the next frame, you've got another exposure of 10 milliseconds, then closes the exposure electronically, waits for the next frame, and so on. So that means you still produce 25 frames per second, but each of these exposure is shortened to allow for enough light, but not too much, to produce a fully, properly saturated video signal. And basically, this is called electronic shutter. Now, that electronic shutter is typically controlled automatically by cameras. Like if you don't do anything to your camera that you get from the manufacturer, you just put it up and don't worry about anything. Most likely, the manufacturers will have set the camera to have automatic electronic exposure, which means the camera is changing this to whatever is taken by the electronics depending on the light. So you can also have the other extreme in terms of low light. So in the bottom drawing here, what we explain is that equally the camera could be default as it comes from the manufacturer, let to have integration mode, so called. So in other words, even though you're producing 25 images per second when you've got sufficient light, once the light drops below a certain level, and that could be anything depending upon the sensor size, the pixel size, the iris, f-stop, and so forth, the camera may decide to go, okay, now I've got not enough light, I need now to make 200 millisecond exposure, which is shown here, or even longer. So instead of 40 milliseconds, which was the maximum in order to produce live streaming at 25 images per second, the camera may decide to go now in integration mode, which means in this illustration here is shown as if you have, let's say, 5 of these exposures. So in other words, the camera exposes sufficient to get good image, but because it's more than 200 milliseconds exposure, depending on the setting, of course, because it's 200 milliseconds exposure, suddenly you are no longer having live streaming at 25 images per second. So what happens is, when you're watching live images, you will see people walking in front of the camera in low light, and you will see nothing that blurry ghost. Because obviously in 200 milliseconds or more, a person walking or running will probably travel half a meter, maybe, depending upon the speed of movement. And that half a meter you will not be able to see sharp, simply because the object was not static. Okay, so that's the important part to consider. So now what we are saying is that by us setting up the camera electronic exposure to not go over certain longest exposure that we basically allow it to go, you can control to have exposures that will not exceed, let's say, 1/500th of a second if you want. A lot of cameras, and I'm not saying all of them, but most of them, will allow you to manipulate the electronic exposure and set it to not go any longer than 1/500th of a second. So if you take 1/500th of a second to be, let's say, 2 milliseconds, so you divide 1 by 500, that's about 2 milliseconds. So you can tell the camera, give me 25 images a second still, like in the top part here, but instead of going to 40 milliseconds, depending on the light, I don't want you to go any longer than 2 milliseconds. And what that does, that actually achieves a sharper image of moving objects, because instead of you exposing them at 40 milliseconds, or maybe 200 milliseconds even worse, you are exposing it only 2 milliseconds. And chances are, if somebody is running or moving, you will see that person or object much sharper than if you did just a normal default setting of the camera, which when it comes from the factory, chances are most likely will be 25 frames per second or 30 frames per second. So that's the idea behind controlling the electronic exposure. And with the ViDiLabs calculator, with the motion blur calculation, we actually tell you, or you can find out, what is the optimum, let's say, longest short exposure in order to achieve a reasonably sharp object and we'll say a few things about what is considered sharp, like how little movement or motion blur you need to have in order to see sharp. And I'll say a few words later on about that. But that's the key to understand, and that's the key that is behind understanding electronic exposure in general. And this applies to really any camera, even though we are discussing here CCTV cameras. Exactly the same principle applies to video cinematography camera, or even photographic cameras, where you may not necessarily worry about producing video, but you want to just still shot. If you want to capture something moving very fast, let's say Formula 1, you want to take a picture of Formula 1, then obviously you will need to shorten the exposure in order to see it sharp. So let's see now the actual, I'll show you what it looks like in actual practical experience, and I'll do a study case so you can see what it was produced and what we calculated based on our formulas. So here is a picture that shows you this is a road that has got a limit of 50 kilometers per hour, and here is all cars are driving or passing by with 50 kilometers an hour. But the one on the left, in this case blown up, when we expose with 1/30th of a second, as you can see here, the front number plates, you cannot possibly see what it is, and yet the image is sharp. I don't know if you can see in small video that I will produce from this, but let's say this person sitting here looks quite sharp. The objects here are sharp, so it's not like the camera is not focused. It's just simply the object, or in this case the car, moves very fast relative to the exposure. Exactly the same distance, exactly the same road, another car, but we now shorten the exposure to 1,000 of a second. You can see the number plate is quite clearly seen. So we are using now the formulas that we developed for our book, and also we advise this formula to the standards 62676-5 in the camera analysis. This is a formula that we have in our ViDiLabs calculator. You don't need to remember it. It's just simply telling you that the dependency of how much blurriness you've got, which here is shown as projected object speed on sensor. So PV is how many pixels will have image exposed from a moving object at one exposure, and that is proportional to the focal length, which depends on the focal length of the lens. It depends on the speed of the object that moves. It depends on the exposure that camera is set to have, and then divided by the distance to the object that you have, and the actual pixel size. PS is the pixel size, which depend on the sensor physical size and the number of pixels it has. So as you can appreciate, it's reasonably complex in terms of it depends on almost everything, but we do have that all included in there. So I will explain and I will show you how that works. So here it is now a little let's say more generic explanation of that. When you have objects that are moving at a certain angle, and it's applicable to objects moving perpendicular to the optical axis of the camera view. But in real life, we often have, like in this picture, this is at a certain angle to the perpendicular optical axis. Like optical axis would be looking at the center of the screen, so this is at a certain angle. The movement itself is at a certain angle relative to the direction of moving relative to the optical axis. So what I'm saying here is that we now have generalized, and the simple logic is you can break up, if this is a camera and this is the optical axis, and this is the direction of movement, let's say, of a vehicle, of a car, and that car has got certain speed, v, you can break up that speed vector into perpendicular vector v to the optical axis, and a vector h in the same direction as optical axis. So from the camera point of view, you're really only going to see this vertical component of the real speed. And for that to be calculated is very simple. Basically, all you need to know is the angle that moving object takes relative to the optical axis. So from simple trigonometry, you will see that if a car moves at 60 kilometers an hour, and it's 30 degrees relative to the optical axis, then the actual apparent speed that the camera sees is 30 kilometers an hour. Simple as that. So this is what is included in the ViDiLabs calculator version 2, that actually now we can calculate and take into account also the angle. The same explanation, and I'll show you some pictures, applies to people running. Like in CCTV, we often have cameras taking pictures of people passing by, walking slowly or fast or running. Intruder may most likely be running. So if they are doing that, then you certainly can appreciate is the same logic. Whatever speed of running of that person is, as long as you know the angle relative to the optical axis, you can calculate. So for example, if this person runs with, let's say, 12 kilometers an hour, I mean walking pace speed is probably 3 to 4 kilometers an hour. A person can run maybe 30 kilometers an hour, but I've taken this as 12 because I've got some pictures to show you what that looks like. So if somebody runs with 12 kilometers an hour, but it is at an angle of 30 degrees relative to the optical axis, to the camera it will appear as running at 6 kilometers an hour because the sine of 30 degrees, the vector that is perpendicular, is actually 0.5, so you don't get 0.5 times 12 is 6 kilometers an hour. Okay, so that's the basic theory, which is not too complicated, just to understand why angle of movement relative to the optical axis is important. So let me first show you an actual running person example and taken with a video at 25 frames per second by having exposure maximum 1/25 of a second or 40 milliseconds. So this is me running in there, and this is the video that I will just run so you can see what it looks like. Of course, not very fast running, it's just normal running, but it's interesting to see that at 1/25 of a second or 40 milliseconds running, that doesn't look any different than the next video I will show you, which is the same now, but I'm exposing it at 1/250th of a second, which is only 1/10 of the 40 milliseconds. So this will be 4 milliseconds. So the point is, when you look at the normal video, you will not really see a difference because the 25 images a second or frames per second blend into each other, and they produce the video impression of motion video. It is when you are looking for an incident, so you're playing back and freeze it, this is the time where you will see the difference. And here is what I'll show you. So here is now that image cropped and blown up of me running at certain distance from the camera, where this is the blown up face. So you can see, even if you know my face, it's probably very difficult to convincingly say this is Vlado running, right? So just for the purpose of calculation here, and this is what we'll do in the further exercises, I've used here, I've recorded this in a video mode with Sony mirrorless camera. Again, this calculation applies to any camera. It doesn't matter whether it's photographic or CCTV or mobile phones or whatever. So, but we need to enter all the details. We need to know all the details. So Sony Alpha full frame sensor, which means the sensor is 36 by 24 millimeters. The resolution I've set it up to record is 1920 by 1080. The lens I've used is 24 millimeters, and I've measured the distance at this particular time. See here, there are markers I've put on the ground, so I can make sure that my calculation is right. The distance is 3.66 meters. Now here the pixel density is 350 pixels per meter. Now if you remember, I already had a video, and if you haven't seen it, I encourage you to see it. I already have a video that explains about the pixel density with the Australian corrigendum suggestion for the IEC 62676-4 to be 350 pixels per meter rather than 250, which is what is currently in the standard. But irrespective of whether one or the other is what you would like to use, the point is I've used here 350 pixels per meter, and theoretically this is much more than 250 pixels per meter, so really the image should be more than enough clear to me if the exposure was short enough. But the exposure was 1/25 of a second, 40 milliseconds. So if I apply all the calculations that we introduced into the formula, the running speed being about 12 kilometers an hour, the angle I've measured is about 30 degrees relative to the optical axis. So that means the blurriness, the calculator tells me that the blurriness is about 23 pixels, 0.4. So 23 pixels, this is what it looks like. And as you can appreciate, this is not good enough for me to see the person clearly. This is the reason why motion blur is very important to be able to calculate. So here's a next calculation of the same thing. So I've obviously done quite a few different tests. This is with 1/50th of a second, which is shorter, half the time of 1/25th of a second. So this is 20 milliseconds exposure time. This is much better, but it's still not enough to be convincingly, well, okay, maybe this is blood or maybe not, but still we are talking about 350 pixels per meter. And the blurriness here is about 11.7 pixels, nearly 12 pixels. Next one would be, this is much better, because this is now 125 of a second, which means we only have 8 milliseconds of exposure per 25 of each of the frames. So we still produce 25 frames per second, but each one is exposed no longer than 8 milliseconds. And this gives me a blurriness of 4.7 pixels. Now, this is something, so you can see the shirt here, the writing on the shirt. This is something that standard doesn't specify, and we've come up with our understanding of what is the acceptable maximum blurriness, let's call it, in order to identify. Our general opinion, my general opinion from what we've done so far is, if you have less than 10 pixel blurriness, probably your brain will understand what that is or who that is, whether it's a car with number plates or whether it's a person. Obviously the smaller the better, but you can never get to 1 or 0 pixels blurriness, because everything of interest that we have in CCTV moves. That's the sad thing. We either have people or cars or anything that does, especially if you've got PTZ camera, then certainly everything moves and it will be even more difficult. But in any case, this is an interesting illustration to see what 4.7 or 5 pixel blurriness look like. Let's see the next one. This is the last that I will show you. This is even faster. This is exposing only 4 milliseconds. So the writing on the t-shirt is even better. But the calculation shows this is about 2.3 pixels per meter at 300, at density 350 pixels per meter. There you have it. So this is what we have in the actual ViDiLabs calculator. So let me now connect to, just to prove the point, let's connect to this one, which means for this version. So what I'll do is I'm going to connect to my app on my mobile phone. So let me enter the same values like we have on the drawing, on the photo. We have a digital SLR camera, full frame, that is set in 1920 or HD mode. The first thing we need to do here is choose the right sensor. In this case FX, or 36 by 24 millimeters. And again, this applies to any sensor, doesn't matter whether it's a photographic one or CCTV. So we've chosen the right sensor. We have the right resolution, 1920 by 1080. And now we need to enter the focal length of the lens. As you will notice here, the window with the focal length is red outlined, which is by default. So in order to unlock it, we need to lock the distance to scene window by holding our finger for 1 second. So now we can enter whatever focal length we want. In this case, we want to get 24 millimeters. So I put there 24 millimeters. Okay, so I now lock it again by holding it for 1 second, because I need now to set the distance to the actual person running. Because like if this was a real project, we would say, okay, this is the main entrance of a bank. We must make sure if somebody is getting in running or getting out running, seen from the outside, we know the distance. So let's say in this case we've got 3.66, as we said before, 3.66. Okay. So these are the settings for the visual part. Now we need to set the settings for the actual running speed, and as we said, this person, let's say, runs at 30 degrees angle of view, runs with 12 kilometers an hour. So how do we do that? We actually hold 1 second the top motion blur green windows. We enter the motion velocity here to be 12 kilometers an hour. And remember we said 30 degrees angle of view. So we enter 30 degrees angle of view. So the calculation says 23 pixels, but certainly by using the default exposure of 1/25 of a second. But remember we said that here we chose exposure of 1/250 milliseconds. So all we need to do is add a 0 to the 1/25. So we add the 0, and there you go. So what we have now is telling us what we actually showed in the slide, that 2.3 pixels blurriness, which is what it looks like. So this is the appearance of the actual 2.3 pixels blurriness. All right. So now let me show you another real practical example. I did that recently for the purpose of this video. We went on the motorway near Kayama, where I live, and this motorway has got a 100 km/h limit. So chances are more or less all people over there are actually driving about 100 kilometers an hour. Some of them maybe a little bit more, but maybe very little of them would be much less than that. So I took as a 100 kilometers an hour is the vehicles that are passing by. I positioned the camera, as you can see here, this yellow kind of two lines at the tip of this line. This is exactly the position that was marking the car park area for the cars, and I used that in order to be able to find the angle of view relative to the point where the cameras were passing that I wanted to capture. So this is shown here in the actual photograph taken of there. So this is, I'm using now a little bit different, again, full frame camera, but the position of it, as you can see here on the right, was measured to be 32 degrees. So this is something you can do. You have to use some kind of either photo editing software or vector editing software, but certainly I managed to find exactly what is the angle of view, and the center of what I expect to see cars is really where the optical axis is in the middle lane, because the middle lane is somehow guaranteeing 100 kilometers an hour, because people on the left lane are slowing down to get into Kayama. People on the right lane may be traveling even faster. So my purpose was to capture in the middle. So the camera was looking this pole here, exactly in the middle, and the cars were passing here. So that also allowed me, using Google Earth, like here, I actually could measure the exact distance from the point of view of the camera to the actual passing point of the car. So some of them may be a little bit earlier captured later, but I could correct that. Some of them would be 30 degrees, 32 degrees, 33, 31. Some of them may be 20 meters, most of them, some of them 16 or 18, and so forth. But the point is, we actually proved that the formulas and everything are applicable to any. You could use obviously any type of camera to do this calculation. So let me now take one example so you can see what it looks like. Okay, so what you can see here is a car passing a little bit earlier to the pole, so the angle for that reason here is 35, and I found out the distance is not 20 like most of the cars passing exactly the point where it was measured 20, but about 16 meters. Again, there is an error there, of course, but it's pretty good to what we really have measured in real life going through Google Earth. So we know that the camera is very accurate in terms of optics, which is why I basically wanted to do with this. CCTV camera will be a bit awkward to drag over there with power supplies and VMS and whatever. But this proves that the actual calculator will really give you spot on calculation as long as your optics is okay. And in this instance, I'm using Sony camera with Sony lenses, which are always 100% what they say they are. So we're having 36 by 24 mil, which is called full frame, 6000 by 4000 pixels. The lens setting is 47 millimeters, which we can read of the actual metadata from this image. Exposure is 1/50th of a second. Distance is 16 meters. Speed is approximately 100 kilometers an hour, more or less. And the angle that we measured is 35 degrees. So if we take now another screenshot, another capture, just to show you what it looks like. Okay, so I think you can see this. I'm using a photo editing program called Affinity Photo. You can use Photoshop, you can use anything else that you may have, as long as you have knowledge of how to use that. But this is just to show you that in there we do have, you can see here in the right hand corner, we have data, EXIF data so-called. Every camera that is made, digital camera these days, by standards, they offer EXIF data, which actually tells you exactly what is the exposure, what is the focal length, what is the ISO setting, and so forth. So you can see here, the camera I'm using is Alpha 7 Mark III. The lens is, as you can see here, 47 millimeters, which is what is shown in this screen at the bottom, and that the exposure is 1/50th of a second. So clearly this is used in our calculations, and what it looks like, if you zoom in, you can't really see anything, you can't recognize any number, you can't read it. That's understandable, but don't forget we are producing, technically with this we can produce live streaming. If you set the CCTV camera 1/50th of a second, you can still produce 25 frames per second, because 1/50th is shorter than 1/25th of a second. So if we now switch to our calculator, just for you to see what it can calculate. Okay, so now what we are going to do is we are not changing the sensor, because we know it's full frame 36 by 24 mil. Now the resolution we will change here, because this is now a picture taken rather than video recorded. The same rules apply, we just have to change the pixel count, because that also influences the blurriness. So if I now change this to 6000 by 4000, sorry, 6000, 4000 is already preset there. Let's change the actual exposure to 1/50th of a second in this case. Okay, now we've set the lens to be 47 mil. So first, before we change the lens, because the window is red outline, that means it's locked, the distance is not set. Let's put the distance to 16 meters, which was the case in this picture. Put the 16 meters. Okay, now we hold 1 second to lock it. And now we put the focal length to be 47, because we saw in the EXIF data, in metadata, that this is 47 millimeters. 47. And now, top part is, we didn't change anything, but now we should change, because obviously it's a different speed and different angle. In this case, we set, so if you turned it off by holding 1 second, this goes gray and basically doesn't affect anything. Even if it is not turned off, it doesn't affect anything else, but just so we see that like we are starting from scratch, what it will look like. So hold it for 1 second. Motion blur calculation now can be applied. Motion speed, we set 100 kilometers an hour, so we double click there, we enter 100 kilometers an hour there. Okay, now the angle is not 90 degrees relative to the optical axis, but it's 35. Like we showed before, we measured it through the Google Earth and through the alignment. So let's put here 35. And we said the exposure was 1/50th of a second. So this sensor blur 156 pixels is the actual real motion blur, which looks like what I showed you the picture previously. So as you can appreciate, 150 is a lot. There is no way you can understand or recognize what that car is, what's the number plate. Even though, this is an interesting point to make, even though all the calculations bring pixel density 490. Now, we did say that if you press the vehicle LPR, you will see that pixel density should be at least 300 for you to recognize the numbers, but only when the vehicle is either static or is very short blurriness because of the short exposure. So that means we are way above it. We were, remember, we had 47 millimeters here. So this is all interconnected. So we had 490 pixels per meter, but because the exposure is so long, we can recognize the blurriness is 156 pixels. Okay, so that's the first interesting example that was done for demonstration. Now I'll show you another one. Let's take now another picture. So this is a next image. In this one, we've got 100th of a second, so half the exposure of previous one. In this instance, the angle is slightly closer to the center, which is about 32 degrees, which is exactly what we measured when we are looking at the pole behind it. Let's see what is the blurriness here. Obviously, still we can't see the number plate. You can clearly see here, even though it's not magnified. This is so blurry that you can't see it. So what does the calculation show you now? Okay, so the only difference now we need to, because we entered the focal length of the lens, which is 47. Obviously the sensor, we haven't changed anything, so it stays like that. We obviously have different exposure now. We said 100th of a second, so make it 100th of a second. And we said the angle is 32, not 35. So double click there, enter 32. We assume kilometers is still about 100 kilometers an hour because that's the middle lane of the motorway. Most people drive at that speed. So this is much better in terms of half the amount of blurriness than previous picture, which is to be expected. Instead of 1/50th of a second, we have 100th of a second. 72 pixels. This is what 72 pixels look like. I hope you can see this now. So as you can see here, the EXIF data is telling me all that I told you, which is 100th of a second exposure, and the focal length is 47 millimeters. So now if I try to zoom in, not possible. 70 something 72 pixel blurriness. That's what it looks like. Okay, all right, so let's go back now to the next image. Let's go to 1/250th of a second. Okay, so I'm going to open 1/250th of a second exposure. So here the exposure, as you can see, is 1/250th of a second. Same lens, 47. The angle of degree is slightly less because the car is a little bit more to the left, and for that reason also the distance is slightly closer to the camera. I measured to be about 70 meters. So let's see if we zoom in here. Yeah, I mean, again, you can guess, but there is no way you can see what it is. So if I go back now and share the actual ViDiLabs calculator screen, we have first 1/250th of a second. We said distance is 17 meters. Now, as you can appreciate here, we are not changing the focal length because we always use this the same. So we'll lock it, hold it 1 second, because 16 meters now needs to be changed to 17. So let's change it to 17. Okay, and we said the angle of is 33 degrees, if I remember correctly. So let's make it 33 degrees here. So the pixel blurriness there, motion blur, is about 28 pixels. And that was, the appearance of that was like I showed you before. So let's finally jump to something that is a bit more visible. That is, let's say 1/500th of a second. So this is now 1/500th of a second. And as you can appreciate, this is quite clear, I would say, even though there is blurriness there. But see, now I'm just wondering, is it CV or CW? It's 27 LS. It's either W or V. But again, closer to what we want, but not perfect. How many blurry pixels are here? Look, the car looks pretty okay, but certainly that blurriness is a little bit moved. So we're having 1/500th of a second, 18 meters distance, and 32-degree angle relative to the optical axis, the movement direction, right? So let's go now to our ViDiLabs screen. We said now we've got 1/500th of a second. Double click there, enter 1/500. Angle of view is 32. Wouldn't make much difference. We have now the distance, 18 meters. So that tells me that approximately 15 pixels blurriness. So as you can appreciate, that is not that bad, even though it's more than 10. But remember, we said we didn't know whether the second character is V or W. So that means what I mentioned earlier, this is our own conclusion. If it is more than 10 pixels blurriness, chances are it will be difficult. If it is less, then most likely you will make it what it is. So let's finally see the shortest exposure I have in this instance, which is 1,000 of a second. Okay, so this is, as you can see here, 1,000 of a second, 47mm lens. The distance we measured to be 20 meters, so this is almost exactly in line with the pole over there that we said we are going to use as a reference, and that is about 31 degrees. So what we do now, let's zoom in to see how much you can see. Obviously I can see it's quite clear even from this distance. That's almost no question. That's EHM19J, right? So let's see what the calculator says in terms of pixel blurriness. So remember, we have 1,000 of a second, 20 meters distance, 31 degrees. So we switch to the ViDiLabs calculator. So we first change to 1,000 of a second. Okay, the angle is 31. So the distance was 20 meters. There you have it. We have about 5.6 pixels blurriness, and that, as you can appreciate, it's quite acceptable. We can almost recognize the number plate. So basically what it means is, one important thing to say here, I didn't say before, but I did mention something about pixel density, but you see pixel density is now 392. So this is more than what vehicle license plate recognition requires of about, we said our finding is between 300 and 400 pixels per meter, depending on the character size, which means depending on the countries. For Australia, probably 300 is enough because our characters are about 70 millimeters high, but certainly you can enter whatever you want. So in our case, because the distance was 20 meters, the calculation for pixel density ended up being, for these settings, 392 pixels per meter. So that means for the previous calculation that we could hardly see it, we still had higher pixel density than what is required, but because of the movement we couldn't identify or read the number plates. Now with less than 10 blurry pixels, we actually can visually see frozen image. Or if this was obviously a CCTV camera, you would have shorter exposures of 1,000 of a second or thereabouts, and when you pause it, you will see what is the number plate. Now clearly the shorter the exposure is, the less light you get into the camera. This is all good for bright scenes like daytime. As you can see, these pictures were taken in bright daylight, but when you have low light, clearly you can't put 1,000 of a second because there is not enough light, unless there is a really good camera with large pixels. Maybe you can get to that, and with the AGC you'll bring up the images enough to be able to see what is there. For that purpose, it's important to know that industry that use, let's say, speed cameras, for example police traffic cameras, they actually add to their cameras strobe lights, either white strobe lights like a flash or infrared strobe lights. In any case, that strobe light purpose is to allow for the picture taken to be sufficiently of enough strength or good quality, even with 1,000 of a second. And that's usually synchronized, so it's a little bit more complex system, but the concept behind it is the same. So you can achieve, even with CCTV camera, a number plate recognition or reading, providing you understand how to position the camera, providing you understand how much light you've got, and providing you know you're having the best possible camera for that purpose, which in my opinion is, if it is a CCTV camera, should be a camera with large sensor and large pixels, which basically will capture sufficient light even at low light intensities. Or if that fails, you probably will add infrared light or strobe light to add to the illumination in low light. So that's basically all that I can explain for the motion blurriness. As you can appreciate, almost anything can be used for calculating motion blurriness. We actually have, maybe I should just mention that before I close this. Okay, so we actually have made a similar calculation for casinos where people are using roulette wheels, and camera is looking at the roulette wheel, and one of the clients I had in the past was complaining that the patrons were actually complaining that they could not see the winning number, which is projected through a camera on a big screen above the roulette table. Because such a camera would take a picture, but because you need to freeze it in order to see which one to show which winning number, that freezing produces blurry images because the roulette is spinning. So what we did is the same exercise like finding out this car speed movement, or maybe me running in front of the camera. We calculated the speed of the roulette wheel moving. We found out what is the size of the roulette wheel. We did all these sort of tricks. We know which cameras we are using, and this is the picture that actually proved what this is with the previous version of ViDiLabs calculator, by the way. So there is a separate video for this if you're interested, but I'm just highlighting this because it's within the motion blur. This is the image of the roulette wheel of the winning number at 1/60th of a second, and the calculator shows that this is 22 pixels blurriness. Now you will say, well, I can see where the ball is. Yes, that's true, but you can't read what's the number there. And the blurriness is exactly like what the calculator says about 22 pixels. You actually have total of 50 pixels width of that egg-shaped ball, and the ball itself is about 29 pixels going vertically. So horizontally 29 plus 21 is 50 pixels, which is exactly what it looks like, which is why you can't read the numbers. But if we now shorten it, in this instance this was shortened to exposure of about 1/250th of a second, suddenly you see the ball and you can see the number. And this is the same application of ViDiLabs motion blur calculation. So there are a number of different possibilities you can use the calculator. It's up to you how. This is just a couple of examples, but I'm sure you will find out in your own way. And by all means, if you have some interesting application, let me know, because I would like to basically add to these case studies. So thank you for watching. Stay well, stay safe in this COVID time, and come and visit for other case studies which I'll be adding to the YouTube channel and to the ViDiLabs webpage. Thank you again, and all the best.